Hi guys, and welcome to another online version of National 5 Chemistry. Today we're going to be talking about two things. We're going to be talking about and introducing another homologous series called the cycloalkanes, which are very similar to alkanes, so it shouldn't take us long to get to grips with how to name those. And then we're going to talk about something which is related, which is isomers. Okay, so by the end of the video, you should be able to name and draw the full structural formula for the cycloalkanes and be able to understand what an isomer is and be able to draw isomers of different compounds. And hopefully that'll make sense once we talk about isomers. Okay. Right, well, let's have a look at it. First of all, what is a cycloalkane? Cycloalkanes, as I've said, we're introducing another homologous series here, and as I've said, homologous series definition is that it is a group of compounds which have similar chemical and physical properties, and they must have a general formula which can be written for all of them. And the cycloalkanes are no different. That applies to all of them. Okay, they're saturated compounds. Now, what that means is that they contain only carbon-to-carbon single bonds. However, they follow a general formula which we've seen before, the CnH2n general formula. Now, we have seen that before in the alkenes. So they have exactly the same number of carbons and hydrogens as the alkanes do, but they don't have any double bonds. It's all carbon-to-carbon single bonds. So it might be worth just now pausing the video and having a little go drawing a molecule you think fits that criteria. Okay, it must have single bonds, but it must have double the number of hydrogens as it does carbons, no more or no less. And the clue is that they are cyclic. They do not have an end, like a circle. Okay, so that's a clue for you as to how that you would go about drawing these molecules. So they're nothing quite like what we've seen before. If you've had a go at drawing and seen what you come up with, like always, we're going to focus on the first 8. But hopefully you've come to realise that if you've had a go at drawing these cycloalkanes, they can't have a 1 or 2 carbon cycloalkane. And that's because it must be linked up like a circle, okay, with no end. Now, you can't do that with a 1 or 2 carbon molecule. So the first cycloalkane is actually cyclopropane. And it links up, not so much like a circle in cyclopropane's case, but more like a triangle with the hydrogens coming off like that. Okay. So you've got all single bonds, but if you have a little look, you've got double the number of hydrogens as you do carbons. I've got 3 carbons there, and if you count, I've got 1, 2, 3, 4, 5, 6 hydrogens. Now, what that means is my chemical formula is C3H6. Now, pause the video at this point, and what we'd like you to do is have a go at doing the others. Okay, there are 5 others to do, and see if you get the same as me. Okay, so pause the video and see what you can come up with. So there you go. Hopefully you've got something that looks a bit like that. Obviously you can see that they are a bit of a nightmare to draw. So I've had a bit of a disaster with some of them, particularly the bigger ones. Only because I was running out of space. If you're doing yours in a class notebook or in a jotter, you can give yourself as much space as you like. It doesn't have to be a perfect circle by any means. The important thing is that you've got the right number of carbons and the right number of hydrogens, and you can see that in the chemical formula. So if you've got a 4 carbon If you've got 4-carbon cyclobutane, then it must have double the number of hydrogens. So it must have 8 hydrogens. C5, H10, C6, H12, C7, H14, C8, H16. And like I said, that's exactly the same as the alkenes. So this highlights a bit of an issue with chemical formula only. So if you were just given a chemical formula, there's no way for you to know on paper whether you're talking about an alkene or a cycloalkane. Okay, because they both have the same chemical formula. They've both got 3 carbons and 6 hydrogens, for example. The only way to know for sure is if you're given the structural formula. Okay, because then you would know if you're talking about cyclopropane or whether you were talking about propene. Now, that leads on quite nicely to the idea of isomers, because an isomer is a compound that has the same molecular formula but a different structural formula. So in other words, it must look completely different, but it must have the same chemical formula, the same number of carbons and the same number of hydrogens. So we've just seen an example there where we have something like cyclopropane, which has 3 carbons and 6 hydrogens, and we've got propene. Propene also has 3 carbons and 6 hydrogens, but they look completely different. They've got a different name, they're completely different molecules. Okay, in fact, one is a completely different homologous series from the other. So what that tells me is that cycloalkanes are isomers of alkenes. So if you have cyclobutane, for example, then one of its isomers would be butene. Okay, exactly the same. It doesn't matter which one you've got. The other one with the correct number of carbons is its isomer. Now, there are lots of other examples of isomers, but that's one, a nice easy one. If you're asked to write down an isomer of an alkene, for example, go for the cycloalkane. The cycloalkane is the go-to one there. Okay. Sometimes you might be asked to give more than one isomer of an alkene, in which case you're a bit stuck if all you can come up with is the cycloalkane, because that's only one isomer. Let's have a look though at, say, hexene. Okay, so we've got hexene. I won't draw in all the hydrogens here, but you always will. So hexene has 6 carbons, C6, H12. We know that one of its isomers is 1, 2, 3, 4, 5, 6 cyclohexane. Okay, let's draw in the hydrogens here. I'm not going to be lazy. Draw in all the hydrogens. And you'll see that as I'm drawing them in, I've drawn 12. So that's one isomer. But let's say you've been asked to name 2 isomers. Okay, no, you're a bit stuck now. Actually, another way to make an isomer of an alkene is to move the double bond. Now you need to be careful with this, and I'll show you a couple of examples where that won't work. But in this one, because it's a nice long alkene, what we can do is we can move the double bond in one. So if we have 1, 2, 3, 4, 5, 6, running out of space here. What we've done is we've changed, I've put in an extra hydrogen there. So let's ignore that hydrogen, forgetting my own rules. If we look at that, we've still got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So it's still C6H12, but I've moved the double bond in one. So that's no longer hex 1ene, it's hex 2ene. So again, I've changed the way the molecule looks, I've changed its structural formula, but its molecular formula has stayed the same. So that's another isomer. Now you need to be careful when you're looking at alkenes with that, because there's a couple of examples where that won't work. For example, if you have a shorter isomer, a shorter molecule, such as if we take propene, for example. Okay, we've got our hydrogens in there. If you move the double bond, the only place you can move it to is in here. So what you've got is that. If you look closely, those two molecules are exactly the same. You haven't changed anything at all. Because if you think about it, all you've done is flip the molecule. Imagine taking that page and turning it over. You've just flipped that same molecule. Both of those molecules are prop 1ene. Because remember, the double bond, we need to start counting with the end closest to the double bond. So both of those molecules are exactly the same. So they are not isomers of one another. Okay, you need to be careful of that. The other thing that you can do, particularly with the alkanes, because the alkanes, you might think, well, how can I draw an isomer of an alkane? Because they're the only homologous series with the general formula CnH2n plus 2. There can't be any isomers. Well, actually there are, because you can add branches. Okay, all you need to make sure is that there's the same number of carbons and hydrogens. So let's take hex. Oh, I've moved that forward. Oops. Hexane. Okay, so let's take hexane again. Okay, so we'll take hexane, which is the alkane version of hexene. 1, 2, 3, 4, 5, 6. And we will put in our hydrogens. Now, all we need to make sure is that whatever we draw, it has a completely different structure, but it must have C6H14 as its molecular formula. So let's draw something that's got 5 carbons in its long chain. And right in the middle of the molecule, I'm going to stick a methyl branch. Now it's got 6 carbons. So there's my C6. What about my hydrogens? Let's make sure all my carbons here have hydrogens around it, including my branch. 1, 2, 3, there's 4, 5, 6, 7, 8, 9, 10, 11, 12, 13 and 14. C6H14. So those are isomers of one another. So adding branches to alkanes is another way that you can get an isomer of an alkane. In fact, it's the only way that you can really get an isomer of an alkane is to add a branch. Again, word of caution, because with the shorter alkanes, you can't really do that, because if you add a branch, you need to make sure that the branch is going to the middle of the molecule. You're chopping a carbon off and you're moving it to the middle of the molecule. If you just add another carbon onto the end, you're not creating an isomer. All you're doing is creating a bend in the molecule. And we've looked at that before when we've been naming things. And a few of you fell into that trap of, actually, that's not a branch. It's just that the molecule is a little bit bent. Okay, and we need to count that as part of the long chain. So you need to be careful of that as well. Okay, because what you might end up doing is drawing exactly the same molecule. So I'll give an example. If I take hexane again, if I were to draw 1, 2, 3, 4, 5, 6. First glance looks like an isomer, but actually I've not really created a branch, because there is no split in that molecule. There's no choice of direction. That it's one straight chain. It's just got a little bend in it. Okay, so be careful of that. Make sure if you're adding a branch, add it to somewhere in the middle of the molecule. Okay. All right, let's have a look. We're going to do a little quiz now. You're going to see two structural formula. Pause the video and determine whether you think they are isomers of one another. When you're ready to find out the answer, press play again. I'm only going to give you a short time to pause the video, so be ready with the pause button to pause the first one. Okay? Okay, here's the first one. Pause that video. Okay. Are these isomers of one another? The answer, yes. Hopefully you got that. If you have a look, we'll see why. We've got 4 carbons in the long chain, and we've got 2 carbons up here. So that's 6 carbons in total. That's an alkane, so that means that I've got 14 hydrogens altogether, and you can count them if you're unsure. Okay, so that's a C6H14. Over here, I've got 4 carbons in my long chain. I've got 2 carbons here, making a total of C6. It's also an alkane, so it's also H14. The difference is that in this one, the branches are on carbon 2 and 3. In this one, both branches are on carbon 2. So it looks different, its structure has changed, but its molecular formula hasn't. Okay, let's have a look at the next one. Are these isomers of one another? The answer, of course they are. Why? Well, this one, it's butane. It's a straight chain alkane, C4, H10. In this one, it looks first of all like it's got 3 carbons in it, but actually there's a carbon up here. That's a methyl branch, so it's got 4 carbons. It's also an alkane. Count the number of hydrogens, and it's going to be 10 hydrogens. So both are exactly the same molecular formula, but their structures are different because this one has a branch. Okay. What about this one? Pause the video. Let's have a look. Okay. Are these isomers? Yes, they are. Let's have a look and see why. Well, in the left-hand one, we've got 1, 2, 3, 4, 5, 6 carbons, 5 in a long chain, and one methyl branch on carbon 2. If we've got 6 carbons, if we added all the hydrogens up, because it's an alkane, we would have 14 hydrogens. Here on the right-hand side, we've got 4 carbons in a long chain, but we've got 2 methyl branches on carbon 2 this time. We've got one down here and one up here, bringing our total to 6 carbons, and if we add all the hydrogens up, we've got ourselves 14. So both are C6H14, but both have different structures and different names. So they're isomers of one another. Well done if you got that. What about this one? Okay, be careful with this one. Let's have a look. At first glance, you might think, oh yes, they're isomers of one another, but be careful. Remember, on the left-hand side, you've got an alkane. On the right-hand side, you've got a cycloalkane. Remember, the general formula for the alkanes is CnH2n plus 2. That's the alkanes. The cycloalkanes, CnH2n. So they cannot be isomers of one another. Let's double check it. We've got 4 carbons, C4, and we've got 10 hydrogens, H10 over here, and here we've got 4 carbons, C4, H8, 8 hydrogens. So their molecular formulas are different as well as the structural formulas, so they can't be isomers. Okay, no. Last one, a little bit more difficult. Let's give it a go. Are these isomers? Yes, they are. Let's draw them out. We need to draw these ones out. I would always recommend it. So but1-ene, we've got 4 carbons with a double bond on the first, because it's but1-ene. 3-methyl, we've got a methyl branch on carbon 3. Let's put in our hydrogens. Okay. That means we've got 1, 2, 3, 4, 5, or C5. H, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. As we would expect for an alkene. Pent1-ene, well, we've got, that means it's a 5 carbon molecule, pent, and it's got a double bond on carbon 1. Let's add in our hydrogens, and you can see you've got C5, H, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Molecular formulas are the same, but their structural formulas are very different. One has a branch, one doesn't. So if you get them like that, where it's just the name, I always recommend you draw them out, because it's then very easy to see. Okay. All right. I hope that makes sense. Go back and look at things if you're not entirely sure. It's tricky when you at first. Try as many as you can, and the more you do, the better you'll get. And I will see you next time. Thanks very much, guys.